In this video again something about developing a Class B amplifier. I have already made an earlier video and I will give the link in the text box. By the way, all these videos are, say, in a certain way videos that show flaws when you want to develop yourself such an amplifier. And I want to develop a Class B amplifier. Why is that important? That is important because in a Class B amplifier, the current that is drawn out of the power supply is directly related to the amplitude here on the input of the amplifier. So for instance, when you disconnect here the signal generator, it's here now, and we are in the we are in the 300 Hertz range, and on the scope we see this at the output of the amplifier. But when I remove the signal here, we see this, of course. The signal disappears, but more important is that also the supply current here falls back to almost zero. Falling back to almost zero, that has everything to do with, say, a kind of quiescent current that is necessary to prevent crossover distortion, and perhaps I will give more information about that in this video. Working now at the moment on approximately 18 volts, so let's give the amplifier again a signal. So now we have a certain frequency, and I want to show, say, the typical problems that you can get. At first, perhaps this is interesting to know. The basis of this thing, the amplifier that I'm showing now, is here. It's in my book Schematics to Audio Amplifiers and Loudspeaker Boxes. It is, when you study it more closely, a kind of op-amp circuit. But an op-amp circuit that can give out an audio signal in the order of 1 to approximately 3 watt. Best voltage is between 12 and 20 volts. We want to know more? Buy my book. Anyway, so in the first video about this circuit, these two end transistors here, this one and this one, were active. And this was in the first video an NPN transistor, NPN end power transistor. This was a PNP transistor. So I did many experiments. I really got it working. But the problem was that the quiescent current was too high. And the quiescent current is always very important. When such an amplifier takes a quite high quiescent current, there is no crossover distortion. But when the quiescent current of such an amplifier is pinched off, and I will tell more about it, you see crossover distortion. I want to demonstrate that here. I only can demonstrate it now with this setup. So these two end transistors are not active. I hope to make another circuit in the future where I use this transistor and that transistor as a Darlington, a power Darlington. Anyway, here are two diodes they are responsible for how much crossover distortion you will find in the circuit because of their voltage drop. They are both silicon transistors. They have each a voltage drop in the order of 0.7 up to 0.8 volts. So together 2 times 0.7, that's approximately 1.4 volts. But when you have a Darlington here, so another transistor is that must be driven, that voltage drop here must be higher. And that voltage drop is very critical, and in many schematics, in books, etc., you see here sometimes a potentiometer to set the quiescent current in some way. There are also circuits with a transistor, where a transistor is used as a kind of Zener diode, and by varying the voltage on the base of the transistor here, you can set say the quiescent current in a broader voltage range. Anyway, here you see these 2 diodes. This is one, and here the other one, and I've bridged one of them with a crocodile wire. So let's see what happens when we take out that crocodile wire. At the moment you see nothing. That means that such a circuit can be operated with 2 diodes here 2 diodes, but also with 1 diode. But what happens when we lift up the supply voltage? Now it's say 16 volts. We go now to higher voltages. Now we are on approximately 30 volts. Still nothing happens. Of course, that has everything to do with the demonstration, but anyway, no problem. So let me try to make this circuit dysfunctioning. Now, by the way, there are 2 diodes that give a certain voltage drop. I shut out now one of them here. Well, that was the issue. I shut now out one of them. So now we have only 1 diode here, not 2 diodes. And here you directly see the crossover distortion here by this kind of bulb in the middle of the sine wave. And of course there's also, say, a difference when we go to other frequencies. This is, say, in the like I told, in the, let me go to a very clear situation. This is 400 Hertz, and now we are on 4000 Hertz. Let's see. Still we have, again, we have different problems, by the way. Here there's a broadening in the wave. Here there is crossover distortion. Here there is oscillation. That means that here on this line, that this part of the circuit here, this part of the transistor circuit doesn't work properly, and there can be made changes. For instance, changing the value of this resistor. This is now 680 ohms, but that was for 12 to 20 volts, and now we are on approximately 40 volts. Here we see the current that it takes. It takes approximately 500 milliampere. Does that mean that we have an audio amplifier of say 15 watt? I don't think so. Here the lamp that is used as a loudspeaker. That's quite good idea, though of course such a lamp is only a resistive load to such a audio amplifier, and in reality a loudspeaker is a coil with inductance and capacitance, etc., etc. And such a lamp as a load for an audio test load for an audio amplifier doesn't have capacitance or inductance anyway. Again, about the quiescent current. You see what the circuit takes when a signal is applied to the input approximately 40 volts. Let's take out the signal here, and now we can see that there is still a quiescent current, but it is very low, and I think that's okay. So signal is gone. Quiescent current is dropped down to a very low value. Of course, you must measure that with a milliampere meter, not an ampere meter anyway. Let's apply the audio signal again. And now we see this. Well, that these things have everything to do here with the, say, when the transistor heats up. I think now you can see it, the heatsink is extremely hot. And we know often there's a kind of trick. Mount the diodes, these two diodes that are responsible for the quiescent current, on the heatsink so that they are heated up. That sometimes can help. Anyway, take away the audio signal again. Put on the audio signal again. And let's also see what happens when we bring down the supply voltage. In many cases that works very good. The amplifier gets more stable. Now you see that it gets more unstable. There you can directly see it. Anyway, let's bring down the voltage, supply voltage, to a more human value. So now we are here, and this seems to be 12 volts here, 500 milliampere, and this seems to be a somewhat better waveform. The oscillations are more or less gone. Of course, the input signal is critical. I will also change that now to a lower input. So here we have, I change now the input level to approximately 100 millivolts. So now we have again kind of, say, good, healthy situation, though here there are still, say, there's still visible the crossover distortion. Anyway, let's go to the lowest frequencies. Many amplifiers don't have good properties on low frequencies. Well, this is, I think, quite good. This is 400. Let's go to 40. Also quite good. And here you see distortion, by the way. So let's bring down the input level somewhat. The distortion is gone. Now the amplifier is overdriven on its input. So the input level is also critical. Well, that were more or less some considerations. I can surely talk more about all the properties of such a circuit. For instance, that we have here a Darlington. That's important. The whole circuit is an Opamp. The value of the capacitor is responsible for the maximum bass frequencies. These two values are responsible for the bass frequencies, and here with these two resistors you must set the Darlington, in fact the first transistor, or in fact the whole Darlington, to its proper working point, to its proper bias. These two transistors are responsible for the bias of this circuit. And furthermore, I will try to develop it further to get to a good amplifier, and also want to use these two transistors here, these two ones, to get much more energy out of it. And well, this is interesting to show. Here, for instance, we see oscillations on the say where the sine wave goes through the zero. Has everything to do with the two odd end transistors. So, and furthermore, so these are problems that are solved when you want to develop an audio amplifier in a second or third or fourth stage. First stage, I showed it in this video. But when you want to keep it simple, make this properly working, 1 to 3 watt audio amplifier. And don't forget to set the right bias here by doing some experiments with these first resistors.